Welcome guys to the last of our Marshmallow chemistry videos. Today we're going to be looking at haloalkanes and stereoisomers. So we're going to start with our haloalkanes. In this video we're going to be using the large pink marshmallows as carbons, the small pink marshmallows as hydrogens, and the green small marshmallows as halogens, more specifically chlorine. The function or the formula for haloalkanes is Rx, or we could represent it as a CX, showing that there is something connected to carbon. The X is representing a halogen, given the name haloalkane. For those who have forgotten, halogens are everything in group 17, so that is fluorine, chlorine, bromine, iodine, astenine, and tennessine. Here we have 4 methane compounds with chlorine attached. In our first one we have a single chlorine attached to our methane, as you can see by the one green marshmallow. The second, we have 2 chlorine atoms attached to the methane, 3 in the third, and 4 on the last one. These are all considered haloalkanes. When we come to name these, we look at the number of chlorines or the number of halogens on each of our molecules. So the first one has a single chlorine, so we call it chloromethane. The second one has 2 chlorines, so we give it the name dichloromethane, di representing 2. The third is trichloromethane for the 3 chlorine atoms, and the last one is tetrachloromethane. For the prefixes that show the number of chloro on each one, there is no need to have a number representing 1 chloro, so it's just a single chloro. The others follow an obvious pattern: di, tri, tetra, penta, and so the last thing we're going to look at are stereoisomers. Earlier in the course we looked at structural isomers, where they differed because the arrangement of the atoms was different in each molecule. Stereoisomers are a little bit different. The atoms are connected in the same order, but the orientation changes, meaning they end up being different molecules. There are 2 types of stereoisomers, geometric and optical. In our course, we're going to focus on geometric isomers. These are stereoisomers where the functional groups are locked in place by a double bond. Because of the nature of the double bond, it does not allow the carbons to spin around, so the carbons are locked in place. The first molecule we're putting up is an ethene molecule. You can see the double bond between the 2 carbons. You also notice that there is chlorine atoms on either side of the double bond. This is referred to as a trans isomer. Trans means opposed or across from each other. So the chlorines are across the double bond. Our second molecule is an ethene molecule again, with chlorines on the same side of the double bond. The word we use to show that is cis. So this is a cis isomer. It also, if you have a look and use your imagination, makes a C shape from the way the atoms are across the double bond. When we name these things, we look at the overall molecule. Both of these would be 1,2 dichloroethenes, because there is a chlorine atom attached to the first and second carbons. The first one, because it is a trans isomer, we put the prefix trans at the front to show exactly where the chlorine atoms are. The second still is a 1,2-dichloroethene, but they're on the same side, so this would become a cis isomer. Okay guys, that is us done for our videos on organic chemistry.